Everyone. Yesterday I made about an hour-long lecture video, I called it Lecture 17, for my Applied Stats course at Bethel University. It's really an advanced undergraduate stats course that's calculus-based, talking about simple linear regression. I will post a link to that video down in the description below. It might be helpful to watch that video if you're not real familiar with the formulas involved with simple linear regression. In that video, I went through a PowerPoint related to an example and showed a bunch of formulas and showed the answers to those formulas in the context of simple linear regression, like what is the regression line, what are confidence intervals to predict the mean, and that kind of thing. But I said to my students and to anybody else watching that you should check those answers on your own, and that would be a good exercise to do. In this video here today, I would like to actually go through the details of the calculations for 3 long old exam problems that I've given. I've given these kinds of exam problems in both non-calculus based and calculus based stats. You don't need calculus to do these things. You do need to understand how to read spreadsheet output, for example, and use various formulas, and how to interpret what's going on with simple linear regression. So let's start with this first problem. I should start with a caveat, however, with this first problem, in that it is not really an ideal problem to which to apply statistical inference in the context of simple linear regression, generalizing from a sample to a population. However, we will do so anyway, and many people often do so anyway, even though it's not really the ideal situation for a simple linear regression model for statistical inference from a sample to a population. Let's go ahead and go through the details of reading the output and using formulas. I know the numbers might look kind of small. I will zoom in as necessary if you're having a hard time reading it. The problem says the Leaning Tower of Pisa was reopened to the public in 2001 after being closed for 12 years because it was in danger of collapsing. Some engineers took steps to prevent that. Data from way back in the 1980s show the amount of lean in the tower in millimeters in terms of the year. These were evidently actual measurements. Actually, I modified these numbers a little bit to not be the exact numbers. I've got some summary statistics in this line right here. I've got the mean of x bar, that's the mean of these years, standard deviation of the years, the mean of the y's, the lean values, and their standard deviations, and the correlation between x and y, that's r. In addition, we see down here regression output like you would get from a spreadsheet if you use something called Excel Minor Analysis Tool Pack to get this. You've got some regression statistics here, an ANOVA table here, and information about the slope and intercept here. Okay, I'll explain what we need out of this as we go. The first question says, here part A, what is the equation of the regression line for these data? And describe the real-life meaning of the slope. We want to interpret the slope, which does mean you want to think about units for the slope. Okay, this is an appropriate kind of thing to do. This is not really statistical inference at this point. We are going to use statistical inference later in the problem, even though it's not really an ideal situation for that. So as far as answering this question, definitely the best way to go, if you got this spreadsheet output, is to use these numbers right here. That's going to be the quickest way to get the answer. Let me zoom in on those numbers again. You can see the first one is labeled with the word intercept. It is the intercept of the regression line. It would be what we call b sub 0. The second number, is that the slope? Well, it's not labeled with the word slope. However, it is the slope. It's next to the x value, which is the year. It's good to not necessarily label this with the word slope because you want to remember what the explanatory variable is. In this case, it's the year. And when you do multiple regression, you're going to have even more lines here, and you're going to have more than one explanatory variable, and you want to have the names for all of those so you remember what they mean. Again, this is labeled b sub 0, and this is labeled b sub 1. That's the intercept and the slope of the sample regression line. We're thinking of this as a sample from a bigger population where the population would be, say, all the years between maybe 1970 and 1990 or so. Again, that's not really an ideal situation for inference, but that's one way to imagine this. What's the equation of the regression line? Well, it would be y equals b0 plus b1x. It's traditional to put a hat above the y. to emphasize that we use the regression line to predict y when we know x, to estimate y when we know x. That's a common thing, to put a little hat above the variable when you're trying to emphasize it's used for prediction. So now we plug in the numbers, and I will go ahead and just use fewer decimal places than you see here. 1531.9, well, maybe I should use all of them. That would go against my advice from yesterday. Use as many digits of accuracy as you can as you go, and then only round at the end. That's the intercept plus the slope, 0.7257142854 times x. That's the equation of the regression line, and yeah, you can round it, but that's fine as well. This thing is the slope. What is its real life meaning? Slopes are always rates of change. The rate of change of y with respect to x. Think about the units. Y is the amount of lean in millimeters. That's back up here. X is the year. So this is the rate of change of y, the lean, with respect to x, WRTX, the year, in millimeters per year. And ideally, you'd even add more to that. You'd say, in other words, for every year that goes by, the tower leans another approximately 0.73 millimeters on average. Not necessarily exactly, but on average. If you calculate the change in the lean from year to year, taking all these data into account, and it looks like it's leaning more in that year from here to here and from here to here than in these years, for example, the change is more. On average, it would be close to 0.73 for that change. Okay? Not exactly, but somewhat close. All right, part B says use the regression line equation to predict how much the tower leaned in 1987. This is emphasizing the use of the regression line, or at least one use, to predict an individual y value when you know x. So what you do is you do plug in x equals 1987 into the regression line equation in place of x and simplify. And you'll get an answer for the lean in millimeters. What should we expect for the answer? These numbers for the lean keep getting bigger over time. We should expect a number bigger than all of these. Perhaps 2973 something, or maybe even 2974 something. This is extrapolating beyond the data set here, which can be dangerous, but it seems somewhat reasonable in this case. So it's not necessarily a bad thing to do. The r squared value here is relatively close to 1. That's called the coefficient of determination. It's a pretty strong linear trend. It's not too much extrapolation. I think it's going to be fine. So anyway, now we're going to go ahead and plug 1987 into that equation. And you'd go ahead and write it all out down here. I won't bother doing that. I'll just show you my calculator work. So I've got 1987, I'll do this part first, times 0.7257142854. That gets multiplied by 1987. And then add on this number plus 1531.904762, and definitely round at this point. Approximately 2973.9. Here we want to round 2973.9. Don't forget your units, millimeters. That would be your approximation based on this regression line equation for how much the tower leaned in 1987. Now, was that the actual lean? Probably not. You'd want to go back and look at the data. Part C says, use the chart above to give a 95% confidence interval for the slope beta 1 of the population regression line. And I am emphasizing the population consists of data from every year. It's a somewhat valid kind of inference. More ideally, when you're doing inference with regression, for each x you have lots of y values, or at least when x is close to various numbers you have lots of y values. That's a more ideal situation for regression inference. We'll go ahead and apply it here, even though it's not quite as ideal as that. We only have one y value for each x. So it's, again, not quite ideal, but we'll go ahead and do it. We still can do it. As far as using the chart, it's pretty easy. You got to know where to look. You look on the line for the slope. We are talking about the slope, and you see a lower 95% and an upper 95%. These two numbers here and here are left and right endpoints, lower and upper bounds for a 95% confidence interval to estimate the slope. It's a population slope. Beta 1, not B1. We're not trying to estimate B1. We know what B1 is. That's our sample slope. We're trying to estimate the population slope, beta 1. And the output just gives it to us. Okay, so we can just say the answer is approximately, let's say 0.47 to 0.98. It's an estimate for a slope, so this would be in millimeters per year. Okay, same units as the slope of this individual number up there. This is centered on about 0.725 or 726, and you could double check that. Is there any other way this could be found? Yeah, but that's what I showed you just now is the easiest way. How else could it be found? There's a formula you could use. You take your point estimate, B1, and go plus or minus a t value from the t distribution with a certain number of degrees of freedom times what you could call the standard error for B1. What is the degrees of freedom here? With simple linear regression with just one explanatory variable, one predictor variable, the degrees of freedom is n minus 2. N is 6 here, that's n. N minus 2 therefore is 4. The df for the residual is the degrees of freedom for the regression. And again, with simple linear regression, it's always n minus 2. When we go to multiple regression, then we get n minus 3 or n minus 4 or n minus 5. That kind of thing can happen. So the degrees of freedom here is 4, and I want 95% confidence, so I do need to either use my calculator or use a table to find the t value that I need. This would be labeled, by the way, typically t sub 0.025 to emphasize the area to the right of it under the t distribution would be 0.025. That's what you would do with 95% confidence. The alpha would be 0.05. You divide that by 2 to get the 0.025. If you're not used to that notation, don't worry too much about it. Again, there are 4 degrees of freedom. So here's a t-table, 4 degrees of freedom. I look for 0.975, which that's the area to the left of the t-value. That means the area to the right is 0.025. 4 degrees of freedom, right there. It looks like t is 2.776. So we'll plug the numbers in here. B1 is the 0.7257. I will do a little rounding right now. Plus or minus 2.776. What's the standard error for B1? That can be found under this thing here, standard error. It's this one right there, 0.09233. If I multiply those, what do I get? Again, 2.776 times 0.09233. Looks like my margin of error is about 0.26. It's approximately 0.26. 0.73 plus 0.26 would give you to about 0.99. 0.73 minus 0.26 would give you to 0.47. So with some rounding, I believe it's good enough here. And again, this would be in millimeters per year as well. It's another form of the confidence interval. Part D, we're doing hypothesis testing. So this is statistical inference. So again, this is not really the most ideal setting to do this in. This is especially fishy. But let's go ahead and do it anyway. Write down a null hypothesis, H0, and an alternative hypothesis, HA, often called H1 instead of HA, that the p-value, this small p-value in the chart is referring to. Where is that p-value? It's right here. It's also right here. It's in 2 spots, and that will happen with simple linear regression, that p-value is in 2 spots. I'll explain that later. That's a small p-value. What is the null hypothesis? It's a hypothesis test on the slope, and we're testing for what's called a significant regression. The null hypothesis is that the slope is 0. And the alternative hypothesis, HA, or if you prefer H1, is that the slope is non-zero. It's always by default a two-tailed test here. So that p-value is referring to doing this test. It's a very small p-value, smaller than 5%, smaller than 1%, smaller than 0.5%. We definitely would want to reject the null, and in particular with respect to the level of significance 0.01, because the p-value is smaller. Reject the null. What does your decision mean? It means the null is false, we think, and the alternative is true. We have strong evidence that the population slope, thinking of it as being over all years, is non-zero. So, in addition, the fact that the slope is positive would mean it is leaning more over time. And of course, you could do actually a one-tailed test from this as well by dividing this p-value by 2, and that would be even smaller. So we would definitely reject the null for a one-tailed test, a right-tailed test in fact, and say yes, beta 1 seems to be positive, so yes, the tower is leaning more over time. Since I'm rejecting the null, I'm subject to a type 1 error, where I'd be rejecting the null when it's true. Okay. Now again, this is not really an ideal situation for this kind of inference because we only have one y value for each x value, and definitely these lean numbers are getting larger over time. You could say we're looking at evidence for the lean getting more over time for the entire population of years, say from, again, maybe 1970 to the year 1990 or something. We have strong evidence in that case, but it's still not the most ideal application of inference for regression. On to problem 2. We have some hypothetical spreadsheet output. I call it Excel output, but Google Sheets will do this as well. That you see here, the regression equation is y hat equals 54.6429. That's the intercept plus 0.9451x. That's the slope. And we have ANOVA output here, which was in the middle of the preceding problem, and which we didn't really use, besides just noting the value of r squared. ANOVA stands for Analysis of Variance, and this is about breaking down the total variation in the y values into two components, you might say. A component that's due to the regression line, this 130.0396 is the variation in the y values that occurs because of the fact that the regression line has a non-zero slope, 0.9451, relative to the total variation, that's the 180.1. This is essentially the variability of the y values in the data with respect to their mean when you're not thinking about regression at all. And then there's a missing number in here, an SS that goes with residual error. SSE, I said that was called in the video yesterday, lecture 17. Again, that has a link in the description. We need to fill in the rest of this table, filling in this residual error row. The numbers that go here and here are numbers such that when I add this and this, I get this, and such that when I add this and this, I get this. Okay, so that's pretty easy. You have to put an 8 here, so that 1 plus 8 equals 9. What do you have to put here to make 130.0396 plus it equal that? Well, do a subtraction to figure it out. You can maybe even do it in your head. I'll quickly use a calculator. 180.1 minus 130.0396 is 50.0604. This number here is what I called SSR. That's SSR, sum of squares regression. Its definition is that it's the sum, it's how much are the data varying with respect to the regression line. Let's see here. Actually, how much is the regression line varying with respect to the mean is the best way to think of it. It's that sum of squares. This number right here is what I called SSE, sum of squares of errors. Errors is synonymous with residual. It's unfortunate that both regression and residual start with R. This was the sum of the y values minus the y hat values. I really should put subscripts on these things, not on the y bar, on those things. And this number right here was what I called SST at the very end of lecture 17, sum of squares total. I also called it SSYY. It really means the same thing. Sum of squares with respect to y twice. It's this particular sum right here. yi minus y bar squared. You can think about that without thinking about regression at all. It's related to the variance and standard deviation of the y's. We're not thinking about regression at all when we look at that. And it is the case that SSR plus SSE equals SST. And that's why this is called analysis of variance. These numbers are measuring variability, and we are decomposing the total variability into a regression variability due to the fact that the regression line has a non-zero slope, and error variability, the fact that the points have a random error above and below the regression line. I'm not done filling in the residual error line. I need to also fill in this MS number that goes right here. This 130.0396 I called in the video yesterday, I called it MS sub R. And the number that goes right here I called MS sub E for error. This is for regression, this is for error. These are mean square numbers. You find them by taking the corresponding SS and dividing by the corresponding DF. 130.0396 divided by 1 is 130.0396. 50.0604 divided by 8 is something different. Divide this by 8, it's 6.25755. 6.25755. These are 5s here, it's a little hard to see. Nothing else to do here in part A, though I do want to emphasize that if you take this number, the 130, and divide by the 6.25755, you'll get this F statistic right there. That is this number. I'll confirm that here with the calculator. 130.0396 divided by 6.25755 is, yes, 20.7812. And that F statistic has 1 in 8 degrees of freedom, and you can look it up in a table that it's the corresponding p-value is this, which is a pretty small p-value. And for simple linear regression with one explanatory variable, that is also going to test whether beta 1 is 0 or not. And it's so small we would reject the null again. Part B, what are the values of the regression standard error, S, which I also called S sub E in the video yesterday, and many other people call it S sub E, and the coefficient of determination R squared, which I did talk about once again at the end of lecture 17 video from yesterday. So you need to know some formulas here. S, the regression standard error, which we also call S sub E, is the square root of SSE divided by n minus 2. It turns out that's the formula to use. I've actually already figured out SSE divided by n minus 2. That's this MSE right here, which is 6.25755. I got to take the square root of that thing. Square root of 6.25755. Could also raise it to the 1/2 power. It's about 2.5015. 2.5015 is the answer for the regression standard error. I did talk about in the lecture what this represents is an approximation for what's called sigma, the standard deviation of the y values in the regression model for any given x value. For any fixed x value, you got variation in the y's. We could pretend this is an ideal situation for regression because we don't see the data here. You got variation in the y's in the population. What is the measure of that variability is in terms of a standard deviation of a distribution? It's called sigma. It's assumed to be constant no matter what x is. It's the same for any fixed x. It's the same variability in the y's. And this number is our estimate of it based on the sample, based on the random sample. R squared. R squared is a ratio of one of these SS's to the total SS. Which one? Well, remember, if r squared is close to 1, that's a real strong linear relationship, either with a positive slope or a negative slope. If it's close to 0, that's a weak linear relationship. This, because the residual is smaller than the regression SS, is evidently a fairly strong linear relationship. We have a relatively small residual error. So, to get a bigger r squared value, I'd take SSR divided by SST. That's the general formula, SSR divided by SST. You can also write that as SSR divided by SSYY. And in this case, it is bigger than 0.5. It's 130.0396 divided by 180.1. 130.0396 divided by 180.1. It's about 0.72244. Okay, closer to 1 than to 0. It's a reasonably strong regression, reasonably strong linear relationship. Part C, write down the null hypothesis H0 and alternative hypothesis HA, which again you could call H1, that the p-value up there is referring to, I already said this a few minutes ago, with, once again, simple linear regression with one explanatory variable. It's the same p-value as in the bottom part of the output. And it's the same test you're doing, this two-tailed test right there. With multiple regression, it's going to be something different. Okay, we'll have to talk about that when we get to multiple regression. This p-value is small. Yes, we can reject it at the 1% level even. If it were bigger than 1%, then we could not reject it. So yes, we do reject the null for this example, and we would again be subject to a type 1 error. If we had not rejected the null, then of course then we'd be subject to a type 2 error. Part D. Suppose you know SSXX is 145.6. Calculate the t-statistic for the same test from part C. Confirm the p-value using a table, and maybe I'll try with a calculator as well. There's a couple of different ways you could do this. Choose one, but show your work or explain. So this first way I'm going to show you to do it is a way that I actually did not talk about in the lecture 17. It's the quickest way to do it in this context of, again, simple linear regression with one explanatory or predictor variable, x. T is the square root of the f statistic. T is the square root of f, square root of 20.7812. That's the fastest way to get the t-value here. I'll do it as a 1/2 power this time. 20.7812 to the 1/2 power, about 4.559. That's the t-statistic, and therefore the p-value is going to be pretty small, it would seem. The degrees of freedom we would use would be 8. This is n-2 here. So if I was using a table, I'd look at the 8 degrees of freedom line. 8 degrees of freedom. What was I doing again? I forgot. Let's see. The t-statistic is 4.559. 8 degrees of freedom line. It's bigger than all the numbers past this point. It's between these two numbers. So therefore, the one-tailed p-value would be between 1 minus this number and 1 minus that number. 0.001 and 0.0005. 0005. I'd have to double those numbers to get a range of possibilities for the two-tailed p-value, which would be between 0.002 and 0.001. The p-value would be between 0.001 and 0.002. If you're going to write inequalities with less than signs, put the smaller number on the left and the bigger number on the right. It amazes me how many people forget that's the way you do it, with less than signs, okay? Get the notation right. Okay, so that's one way to do it. Let's confirm the p-value with technology as well as a calculator here. I could, for example, let's try it two ways here. Maybe with the stat menu, let's go to tests and a t-test. Not with data, but with stats here, although will this work? Yeah, I guess this is not going to work because I be using stats that I don't really have. So I guess I would have to do it with a distribution menu here. The TCDF, cumulative distribution function. I'm trying to find the area to the right of 4.559 and double it because it's a two-tailed test. So I'd want to put a 4.559 here for my lower, put, essentially infinity, so to speak, for the upper, 10 to the 99th. DF is 8, paste this. Whatever answer I get, I need to double it. Times 2, 0.0019 when you round that. Yes, that matches 0.0019. Okay? So that would be a way to do it with technology. What's the other way to find the t-statistic? You can use a different formula that was in the Lecture 17 video. It's that t equals the sample slope minus 0, which we don't have to write, divided by the standard error for B1, which is the standard error for regression, S, divided by square root of SSXX, and that's why I gave them that value there. So B1, going back up here, is the 0.9451. 0.9451. S, which we found in part A, is the 2.5015. I'm sure because of rounding, these numbers are going to be a little different here. SSXX is the 145.6. So that's the calculation to do. Let me do the bottom of the fraction first. 2.5015 divided by square root of 145.6. Now take 0.9451 and divide by that. And again, I'm sure my answer will be a little different than the one here, but should be pretty close. I guess when you round it, it's 4.559 still. And once again, we would confirm the p-value. Finally, in this long problem, part E is to find a prediction interval for a value of y when x is some specific number, 24 in this case, using an x star to denote that specific number, because that's what the textbook that I used for that statistical analysis non-calculus based class uses. But we didn't have to call it x star, I could have just called it x. Given the mean, 20.8, given the SSXX is 145.6, just like we had it here. We need the formula for this prediction interval. The point estimate is y hat, which in yesterday's video, I also called that capital Y hat, given that x equals whatever I'm assuming x is, in this case 24. You could write it that way too, as a sort of a fancier but more specific way of writing your point estimate. Plus or minus a margin of error where it's a t value. We're after 90% confidence, so it would be a t sub 0.05 value based on 8 degrees of freedom. I'm going to have to look that up. Times the regression standard error. We're after a prediction interval. These things are wider. This is where in the square root you have the extra 1 plus. When we're doing a confidence interval to estimate the mean, then the 1 is not part of the formula here. 1 plus 1 over n. N is 10, not 8, careful, plus x minus x bar squared over SSXX, where if I'm going to use this x star notation, I'd also put a little star there. The star just means it's a special number. It's not a power or anything. That's the formula to use, and then we do want to interpret the meaning of the interval in relation to the population. To calculate y hat, we need the regression equation. So we need this equation back up here. Plug in x equals x star, the number you're thinking about, 24 in this case, into that. So I need to take, I'll do it all at once here, 54.6429 plus 0.9451 times 24. It's about 77.3253. That's y hat. Sorry about that. There we go. 77.3253 is the y hat. More specifically, it's your estimate for the next observed value y. I guess I'm doing a little interpretation here when x is assumed to be 24. T sub 0.05, again based on 8 degrees of freedom, n is 10, so df is 8. 0.05 is the 1.833 because you got a 0.95 area to the left, therefore 0.05 area to the right. I got the 0.05 by taking the alpha 10% and dividing it by 2. Something you should have done before. Anyway, again, it's going to be 1.860. Was that what I said before? Did I say that one? I don't remember. Yeah, it's 8 degrees of freedom, 1.860 is what T is. S we found up here, it's the 2.5015. Square root of 1 plus 1 over n is 1/10 plus x star is 24. X bar, I'm telling you, is 20.8 squared divided by SSXX. That's the 145.6. 77.3253. Okay, let's figure out the thing under the square root first. 24 minus 20.8 is 3.2. 3.2 squared is that. Divide by 145.6. And then add 1.1 plus 1.1. You get, as always in this situation, a number bigger than 1. Typically a little bit bigger than 1 when you square root it. It's still just a little bit bigger than 1, a little smaller. Multiply by 2.5015 and also multiply by 1.86. 5.0335. 5.0335 is the margin of error. We'd probably want to round these more. You probably better to say 77.3 plus or minus 5.0 even. And then you can find the left and right endpoints as well. I'm not saying what the application is here, but as far as interpreting this, you'd say this is a prediction interval for y. We're 90% confident, based on this sample data, a random sample from a bigger population, that the next time x happens to be 24, y will be in this range here. From, I guess we can do it in our head, 72.3 to 82.3. Okay, whatever the application happens to be. If we were doing a confidence interval to estimate the mean, the 1 plus would not be in there. We'd be taking the square root of 0.17 or so. That square root is going to be in the ballpark of 0.4 or so, and I multiply these, I'm going to get something in the ballpark of 1.5 to 2.5, somewhere in there for this number. It would be a smaller interval, or more confident in a sense in our smaller interval when you're trying to estimate a mean response, a mean value of y when we're given x, than we are in estimating an individual value of y when we're given x. All right, on to the third and last problem. Kind of an interesting example, I think. This is an application that's a little bit more realistic in terms of applying statistical inference for regression, though you'd probably have more data than just this. A study is designed to determine the effects of sleep deprivation on the ability to solve problems. A total of 10 high school graduates are chosen at random. You'd probably want a bigger sample if you were actually doing this. And participated 2 at each of 5 sleep deprivation levels, where these are the number of hours where they did not get sleep before they took the test. I guess they take the test soon after they wake up or something like that. 8, 12, 16, 20, and 24 hours. After his or her specified sleep deprivation period, they're subject to 200 addition problems. These are high schoolers, so they should be able to do them fine. But the number of errors is recorded and the results are obtained. So X, again, is the number of hours without sleep. Y is the number of errors. And you can see, generally speaking, in glancing over this, that the more hours without sleep, the more sleep deprived they are, that the more errors they do make in general. But can we be more precise in making estimates about the population based on these data? I got some summary statistics. And with a calculator, you could plug these numbers into your stats mode, and you could calculate these statistics with your calculator. Before I do the problem, I would like to emphasize how SSXX could be calculated from the other numbers. The formula for SSXX, for example, its definition is this. It's a sum of squares that looks like this. And you could double check that that does give you 320. Turns out that's the same as the sum of the xi's squared minus the sum of the xi's quantity squared over n. And let's just double check that based on the other numbers here from this output here. The sum of the x squareds is the 2880. So this would be 2880 minus the sum of the x's, 160, squared divided by n. What is n here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N is 10. Hopefully this gives us 320. Let's see if it does. 2880 minus 160 squared. Oops, mistake there. 2880 minus 160 squared divided by 10 is indeed 320. Makes me very happy there. Okay, so that's just re-emphasizing how to calculate SSXX. You could also, again, calculate it this way and see that you get the same thing. But you'd have to use the mean, and the numbers would be messier, probably. All right, part A, estimate the line of regression, right? The formulas used. Okay, this is based on a formula I used in yesterday's video, lecture 17. Right near the beginning of the calculations, it's SSXY divided by SSXX for the slope. By the way, in general, this could be negative. SSXY can be negative. It's a sum that's really not a sum of squares. It's a sum defined this way. And that certainly can be negative because in general, the signs of these products here, the factors in the product could be different signs giving you negative products. The shortcut formula for this one looks like this. And you may want to check that this is right as well. Anyway, that's what SSXY is. It could be negative. Slopes can be negative. But in this case, these examples, they're all positive. So when you use this now, you get 152 divided by 320. 2 divided by 320. Double check to make sure I didn't make a mistake. That comes out to 0.475. So there's the slope. The intercept is then found by taking the mean of the y's minus the slope you just found times the mean of the x's. By the way, this equation, defining b0 here, does imply that the regression line always goes through the point whose coordinates are the mean of the x's and the mean of the y's. That doesn't mean that's a data point. In fact, it rarely is a data point. But it always goes through that point, and that can help you draw it if you're trying to draw it by hand. The mean of the y's is the sum of the y's divided by 10. 106 divided by 10 is 10.6. The slope we just found is 0.475. X bar is the sum of the x's divided by 10. 160 divided by 10 is 16. I think this turns out to be a nice number, 3, I believe. 10.6 minus 0.475 times 16 is indeed 3. So your estimate for the line of regression is y hat equals 0.475x plus 3. And actually, now we're using it for something different. Now we're not trying to predict an individual y like we were with the Leaning Tower of Pisa with 1987. Now we're after, in part B here, estimating the mean of all the y's when x is 18. Notationally, that means we also sometimes write the regression equation with a mu hat and specify that it's y given that x equals 18 as well. It's still the same equation, but we're just emphasizing we're sort of thinking about using it differently to estimate a mean instead of an individual y, which is really a little bit more valid application, you might say. Now plug in x equals 18 in there. 0.475 times 18 plus 3. 0.475 times 18 plus 3. 11.55. course, the number of errors has to be a whole number, so you could round this to 12, I guess. And that would be your closest whole number approximation for the mean of all the y's when x is 18. And actually, since it is a mean, we don't really have to do the rounding. If we were trying to do a y hat, then it would be better to do the rounding. But means don't have to be a possible value. They don't have to be a whole number in this case. So 11.55 units would be errors. So for all people in the population whose sleep deprivation is 18 hours, they would make, on average, we would predict 11.55 errors. Part C, find a 95% confidence interval for the mean, not a prediction interval. So here we're using the formula that does not involve the 1 plus inside the square root. We would take this 11.55 errors that we just got, plus or minus, once again, a t. This time it's a t.025 times the regression standard error, s, times square root without a 1 plus in there. Start with 1 over n plus x minus x bar squared over SSXX, where in the previous problem I called this thing x star, but I did not do that here. N is 10, degrees of freedom is 8. So once again, we'll go back to the table. 8 degrees of freedom, 0.025 there, because we're after 95% confidence. Looks like it's 2.306. By the way, I'll show you can get that number with a calculator as well here in a second. 2.306 is what that is. Actually, let's go ahead and do that right away with the calculator. If you go to the distributions menu and look for inverse t, and this means an area to the right, 0.025, so the area to the left, the CDF, is going to be 0.975, 8 degrees of freedom. When I paste this and enter it, it should give me a number close to 2.306. 2.306004133. Yes, very close to that. Okay. What is S? That's the regression standard error. That is given up here to be this 2.241651177. 2.241651177. N is 10. Again, X is, we're talking still about 18 hours of sleep deprivation. X bar we found earlier was 16. SSXX is given up here again. That's the 320. All right, so let's combine all this with the calculator. 18 minus 16 is 2. 2 squared is 4. 4 divided by 320. Oops, 4 divided by 320 is that. I need to add 1/10 to that. Still a pretty small number. The square root is going to be still pretty small, though bigger when you have a number between 0 and 1. You take the square root, it gets bigger. About 0.335 multiplied by S times 2.241651177, also multiplied by T, 2.306. To get a margin of error of about 1.73. So we get 11.55 plus or minus 1.73. That is our 95% confidence interval. We have 95% confidence in this interval to capture the true mean number of errors for all people in the population, even those you don't actually perform the experiment on, who are sleep deprived for 18 hours under the conditions of the experiment, which is maybe that they take the test, I don't know, an hour after they get up or something, okay? Or an hour after their sleep deprivation. I'm not quite sure what they did, okay? Just made that up. And this would be, still you have units of errors. People being sleep deprived for only 8 hours doesn't seem like such a big deal. I mean, I guess you'd have to, if they slept till 8 in the morning, you'd be testing them at 4 in the afternoon. I guess that would maybe be how they do it. Part D, the last part here, almost done. Though it is dangerous to extrapolate, even though we did with the first example, At least if you want to be confident in your answer. Let's do it anyway, just for fun. And many people in the world do use extrapolation, sometimes for fun, but sometimes to even deceive, and sometimes to say, I feel confident that I'm right, even though they might be proven wrong. We can do it maybe for fun. It is likely, in a sense, to be off by perhaps a large amount, and perhaps it's hard to put an amount on the possible error. That's a maybe more dangerous thing about it. Estimate how many errors, to the nearest whole number, a random high school graduate would make if they took the test after being sleep deprived for 48 hours, 2 straight days. So you use the regression equation, plug in x equals 48. Probably be better to call it y hat in that case, because we're talking about an individual student. But anyway, the calculation would be, haven't used red in a while here, 0.475 times 48 plus 3. The model may not really be valid anymore, but we're doing it for fun. 0.475 times 48 plus 3. We'd estimate they'd make, to the nearest whole number, about 26 errors. Okay, that would be our extrapolation estimate based on everything that you see here. Thanks for watching.